Hey, it's Miss Adams from Flamingo Math. Let's look at Lesson 9, Day 1. We're going to have 5 examples today, talking about rational functions, vertical asymptotes, and wholes. In our last lesson, we talked about rational functions as the ratio of two polynomials. And we talked about division by 0, what caused that restrictions from the denominator. Today we're going to turn our attention to looking at vertical asymptotes and finding wholes in the graph. We said a vertical asymptote occurs when a factor in the denominator does not cancel out with the factors in the numerator. But a whole is going to occur when a common factor in the denominator cancels out with a factor in the numerator. And the degree or the multiplicity of the common factors in their location in the rational function will be an important thing to consider in this lesson. In fact, I would put a little star by that. It's going to come back and we will see situations like this in the AP exam. Let's explore that vocabulary before we get into the lesson too much. In this example, you notice that the function has a horizontal asymptote at y equals 1 and a vertical asymptote at x equals 2. So finding that vertical asymptote, you can think about the limit notation as x goes to 2 from the right. So if we wrote out that limit notation, as x approaches 2 from the right on that graph, f of x, we are on this part of the curve, and as we approach 2 from the right, the graph is going to positive infinity. But as we approach 2 from the left, the graph is going to negative infinity. And that's the thinking process that needs to go on when you're looking graphically to answer a question about the vertical asymptote. So we've got a vertical asymptote as x equals 2. You can see here that limit notation of the behavior around x equals 2. On the right-hand side, we want to find the coordinates of the whole. So looking at the limit notation, as x approaches negative infinity, the y value approaches 2. As x approaches negative infinity, we're heading toward 2. As x approaches positive infinity, we're heading toward 2. That's our horizontal asymptote. But they're asking us to find the location of this whole right here, somewhere in there. Looking at the equation, the problem occurs when we factor and x minus 3 cancels out. In order to be able to find the location of the whole, x equals 3 is the problem situation. We're looking for the y value in the whole. The easiest way to find that y value is to take the leftover factors and substitute 3 in for the x value, 3 minus 1 in the numerator, and then 3 minus 2 in the denominator. Simplify that and we find the y value turns out to be 4. So the whole is located at the ordered pair 3, 4. And you can go back and correct this piece here and substitute the y value is 4, the location of the whole. So you found that by removing common factors and then substituting the 0 of that common factor to find the ordered pair for the whole. Here on this slide are some key factors about definitions, graphically what the vertical asymptote means, and that it'll never cross the vertical asymptote, the graph of the function. You can stop the video and read those important facts if you like. We're going to move on. So let's talk about vertical asymptotes and their multiplicity. Here you can see in the first example, h of x, that you could remove x minus 5 from the numerator, and it would get rid of this power 2 and make the power 1. So the denominator had the bigger power, and the denominator is 0 when x equals 5. So x equals 5 is going to be known as a vertical asymptote since the power, the repeated factor, was in the bottom. In the middle, let's see what's happening here. The bottom degrees on that first term, these are both x plus 2 squared. Those cancel out. This is x equals 3. Those both cancel out. And here's x plus 4 to the second. You're going to remove 2 of those powers here. That's in the numerator, x plus 4 to the fourth. That tells us that x equals negative 4 is going to be a 0 of the function. X equals negative 4 is a 0 of the function. And the other situations are all going to be wholes. In the last g of x, it looks like we've got x plus 3 in the denominator. It's going to cancel out one of them in the numerator. So that's going to be a 0 of the function. And we've got vertical asymptotes at the denominator. So x equals 0 is a vertical asymptote, and x equals 1 is also a vertical asymptote. So the first one here, h of x, and the last one, g of x, those both had vertical asymptotes, but the middle one had no vertical asymptotes. So all three of the functions, this is where we had the star, all three of the functions had repeated factors in both the numerator and the denominator. Without simplifying, how could you tell which factors would create the vertical asymptote? So stop the video and think about what you would say to that question. My idea was that the vertical asymptote happened when the factors in the denominator had the larger degree. They did not cancel out. But a hole happened when the factors in top and bottom were equal, or that the numerator power was larger than the denominator power. Let's look at example 1. For each function, determine the x values for any vertical asymptotes. In the first example, you see that we have x minus 4, that's going to cancel. So we would have a vertical asymptote at x equals 3, and we would have a hole in the canceled factor that would be at 4. Not going to figure out the location. In part B, you could simplify that by removing the common factors. We'd get rid of one of the x minus 3's in the top and the bottom, and one of the x minus 1's in the top and the bottom. That would give us a simplified rational function of x minus 1 divided by x plus 3. So vertical asymptote at negative 3, and a hole at the numerator, x equals 1. On h of x for part C, you've got x times x squared plus 5, and only x in the bottom, x equals 0, would produce that vertical asymptote. There would be no hole. No hole, because no x variable in the top. On the last one, k of x, you've got x plus 3 times x minus 3 in the numerator, and factors of negative 6 that add up to 1 would be 3 times negative 2. The x plus 3's could be removed, and this would be our simplified form. So there's a vertical asymptote where the denominator is 0, and there's a hole where the numerator is 0. In the exploration, I factored the numerator and denominator and used my graphing calculator to graph the function in the grid. We want to know what values of x make the denominator 0. That's -1. So that's going to be our vertical asymptote. And I graphed with the calculator and sketched it on the grid. And what do you notice about the graph around the values of x that make the denominator 0? Well, I said it seems to me that the input values approach -1 and the output values decrease without bound. So we could say, using our math language, the limit as x approaches -1 on the function r of x from both the left and the right goes unbounded. I don't need to write two statements, x approaches -1 from the right and x approaches -1 from the left, because as you look at the graph, as we approach -1 from both sides, the branches of the graph are unbounded downward to -infinity. Which leads us to this next slide, the left-hand limit and the right-hand limit. You might want to stop the video and read the details of the input values near an x value and the output values, what's happening to them. Left and right-hand limits will be important topics throughout our course as we proceed. In example 2, we're given a function f of x, and you need to put that on your calculator. We're going to use the values to figure out our table of values. I'm also going to factor the numerator as the difference of two squares, x plus 4 times x minus 4, and then the denominator looks like a perfect square trinomial because 4 times 4 is 16 and 4x plus 4x is 8x in the middle. That's how we know we have a factor that cancels, and that factor that cancels gives us the 0 of that factor gives us the vertical asymptote, which is why we're seeing here we're undefined on that asymptote. Now stop the video and use your calculator to complete your table of values and come back to check your answer against my answers. Hopefully we're in agreement. In part C, for the values near or less than x equals -4, what are the outputs doing? So near -4, they are increasing without bound. And what happens for the values near or greater than -4? They're going in the opposite direction. They're decreasing without bound. So these are increasing, and these are decreasing. And then we can write the limit statement. So the limit as x approaches -4 from the left is going to positive infinity. And the limit as x approaches -4 from the right, the y values are going to -infinity. So we're using the table to answer the questions related to the rational function. Let's see what example 3 has in store. This time we're looking at the graph, and we're going to answer based on the graph. So first, noticing from the table, from the function, we can reduce and simplify by taking out that common factor. That leaves us with 3x plus 1 in the numerator. That's where the 0 is coming from. And x plus 3 in the denominator. That's where the vertical asymptote comes from. In part A, what value has a vertical asymptote? That's at x equals -3. And how do we know? That's the 0 of the denominator. And for values of x near or less than -3, what are the outputs doing? So let's think about that. Near or less than -3, that's over here. They're increasing without bound. So we want to write that here. They're increasing without bound. And the values near or greater than -3, what are they doing? They would be decreasing without bound. That's pretty straightforward. B-O-U-N-D. Okay, let's go look at example 4. In example 4, we want to write a left. Oh no, we're not finished here. I'm sorry. Let's see, evaluate the following limits. The limit as x approaches -infinity is going to be +3. The limit as x approaches +infinity is also 3. That's our horizontal asymptotes. And then the limit approaching -3 from the left is unbounded up or increasing without bound. And the limit as x approaches -3 from the right is decreasing without bound. Now we can move on to example 4. We want to write a left and right-hand limit statement as x approaches 1 for each of the following functions. So what's happening as x approaches 1? We'd have to, from the left, so that's as x approaches 1 from the left. You got to think about what's happening on y. So to the left of 1, think about this, from the left, those are smaller numbers. So a fraction, we've got a negative number and a positive number and then a negative number. So we've got a negative divided by a negative. It's going, the y values are heading to a positive number. So the limit, the left-hand limit, as x approaches 1 from the left, for our function f of x, it's going to go up, unbounded up. In that same idea, as you approach 1 from the right, what would happen? So 1 from the right, we've got bigger numbers than 1. It's still a negative and a positive, and this is bigger than 1, so this is going to be a positive. So a negative divided by a positive is going to give us a positive value. So the right-hand limit, as we approach 1 from the right of f of x, is going to be a negative over a positive. That's a negative. Now, if you follow that kind of logic, turn the video off and try part B on your own, and then come back to check your answers against my answers. I went about this one a little bit differently. I simplified by removing that common factor, and in the first limit, I tried x as 0.9 using my calculator. I got it's almost 2. And on the right-hand limit, I used 1.1, and I also found it was about 2. That gave me the left and the right-hand limit at 1 was approaching 2. For example 5, we want a rational function. We want to create a rational function from descriptions and the graph. So reading carefully, a rational function has the following characteristics. We've got a 0 at 4 and 0. We've got a vertical asymptote at -8 and 3. A 0 of -3 in both the numerator and the denominator. And the limit at a -infinity has to go to -2. So we've got a lot of thinking to do with this one. We want to create an equation and call it r of x. There could be more than one right answer. So my r of x, using what they told us, we've got a 0 at 4, so in the numerator I need x minus 4. We've got a 0 at 0, and we've got a 0 at -3, x plus 3, and we need a limit that goes to -2. So I know I need an x here, but I'm not sure about that, how we can get that -2 in there. In the denominator, we've got a vertical asymptote at +8 to make it -8, and we've got a vertical asymptote at x +3. Okay, so we got an issue. If these cancel out, we still need a vertical asymptote at x equals -3. So I need one more factor of x +3. That means we need, we also need the limit to go to -2. So if you think about it, if you want y equal -2 for the horizontal asymptote, we need to have -2x to some power here divided by 1x to the same power down here. And what's our power in the numerator? Well, you've got 1x here and 1x here and 1x here, so we've got an x cubed in the top and the bottom. So I'm considering the power is going to be x to the third, and that's going to make this factor over here. Get rid of that. We're going to make this become -2x. So I think we can say carefully that we have -2x times x minus 4 times x +3 in the numerator, and then x +3 squared in the denominator, and x +8. I believe that would work. That's one way to get that to work. You can pause the video, enter that on your calculator, and determine if we've gotten everything correct. In this last exploration, it's just redefining how we find that point of discontinuity when there's a common factor, such as x minus 3. We simplified the expression, and then we know that 3 is where the hole is located. You can see it here. And then the procedure is going to be to find the function value at 3 with the simplified expression where that x and this x are replaced with 3, and we do the computation for that. So 3 minus 1 is 2 times 2. That gives us 4, and the denominator is 4. So we are filling the hole. It's like we're filling the hole by removing that common factor up here with the x minus 3. We filled the hole, and this hole is located at the ordered pair 3, 4. And that does support our work. So when x approaches 3, y is approaching 4. And then the last few pages on your notes are just a summary of everything that we've learned with finding holes, vertical asymptotes, and x-intercepts. This is just a reference for you to come back to. And using those examples, we found for the equations that produced a hole, what did we notice about the powers? Well, we found that when the factors are equal or larger, if the factors are equal or larger, powers in the numerator. So that's what would produce a hole. And for the equations that produced a vertical asymptote, what did we notice about the power on the common factors? Well, we noticed that the factors were larger in the denominator. So you may see some multiple choice questions on the actual AP exam that ask you to do this without a calculator, and you would need to remember those rules from this lesson. This is part 1 of our lesson today.